Section 3.4 is about average rate of change, and we'll talk about instantaneous rate of change as well. So what do we mean by average rate of change and instantaneous rate of change? Now let's start with graph number 1. Here we have a graph of a function, let's call it f of x, and we have 2 points here, the point A and the point X, and those are the images of those 2 points. And then we connected those points with a line, or there's a line that passes through those 2 points. This line is called the secant line. Now if we want to find the average rate of change, all what we need to do is to compute the slope of the secant line. That means we find the ratio rise over run. The rise is the distance from this point here to this point here. So this is f of x, the image of x, this is f of x, minus f of a, this is f of a. So this is f of x minus f of a, sometimes denoted as delta f. That's read change in f or delta f. And run, that's the distance from here to here. So this point here is a, this point here is x, and this point here is a. So this distance is x, the final point or the terminal point, minus the initial point, and sometimes denoted as delta x. Delta x is x2 minus x1, or the final point minus the initial point or the starting point. So this is the ratio, which means the slope of the secant line. So slope of the or average rate of change, this is what we call average rate of change. Average rate of change of function f over some interval a, b in general, is the change in f, which is denoted as delta f, over change in x, delta x, and that's f of b, the image of the final point, minus the image of the starting point, over b minus a. And here in this case, this is a, this is b. Now if we are interested in finding the instantaneous rate of change or slope of the tangent line, now look at this graph 2. We have same function. The function is f of x, and at some point a, we want to find the slope of the tangent line. This is called tangent line because it touches the curve of the function f of x at specific point A. So this is called tangent line. And if we want to find the slope of the tangent line, then we need to approximate it here. How to approximate it? We start with some points like point X here, and then find the image of this point here. Then we connect those 2 points P and Q with the first line here. Let's call this line 1. This is a secant line, but it approximates the tangent line. It's not a good approximation though. Now if we choose another point that's closer to the point A, it will have this image. I mean, this point here has this image. Let me choose a different color. This point here has this image, and we graph a secant line. Let's call this L2. As we can see, this is a better approximation than L1. So the secant line can work as an estimator of the tangent line. Let's use choose this point here that's closer to A than the previous point, and then we graph a secant line that crosses through those 2 points, and that L3 is slope of L3 is a good approximation of, or another approximation of the slope of the tangent line. So as you can see, as we are approaching, as x approaches A, what happens to the lines, the secant lines? The secant lines approach the tangent line. So as x approaches A, the specific point, what happens to the images, or what happens to the lines, the secant lines? They approach the tangent line until we get very close to the point A. Then we get a very good approximation of the tangent line, or the slope of the tangent line. And that's what we call instantaneous rate of change. I mean, instantaneous rate of change, we are interested in finding the rate of change at some specific point, at the point A. But for average rate of change, we were interested in finding the average over some interval. So that's the main difference. When we talk about average rate of change, we are talking about slope over slope of the secant line over some interval. And when we are talking about instantaneous rate of change, we find the rate of change over at specific point. That's why we call it instantaneous. Now, how to find these? Let's take some examples. But before that, let me focus on a point here that's very important. Instantaneous rate of change of a function f is closely related to the slope of the tangent line at that point. Good. Now let's start with the first example. In this example, we have a particle moving according to this function, f of t equals t cubed plus t, where t is time, and this is the distance function. The function represents the distance traveled at time t. We want to compute the average velocity. What do we mean by average velocity? Average velocity is change in the distance over change in time. So its average is an average rate of change. So how to find this? Average velocity is change in f over change in time. Because f represents the distance. Now what is change of in f? It's f of b minus f of a over b minus a. I just use this formula here. So what is a and b? A is 1, b is 4, so we have f of 4 minus f of 1 over 4 minus 1. Now we plug these values. F of 4 is 4 cubed, we plug here, plus 4, minus f of 1, we plug it here as well, so we get 1 cubed plus 1 all over 4 minus 1. 4 cubed is 64, plus 4 68, minus 1 plus 1 is 2 over 3, so we have 66 over 3, which is equal to 22. For example, meter per second. So that's just unit. This is the average velocity, or average rate of change, and change of velocity over time, I mean. Now, if we want to find or estimate the instantaneous velocity at specific time, not over interval, but at specific time, at time second 1 or minute 1 or hour 1, at specific time. So how to find that? In order to find that instantaneous velocity, we need to pick another point, because we are using the formula for the slope, and to apply that formula we need 2 points, and here we don't have another point. In the case of average velocity we had 2 points, but here we are given just 1 point. So the other point, so this is A, we want to find another point X or B, but it should be very close to 1. Let's choose 1.01. This is very close to 1. Now we want to find the average, the instantaneous velocity, so we apply same formula. So instantaneous velocity, f of b minus f of a, b is 1.01 minus f of a, which is 1, over 1.01 minus 1. So same formula, but the difference here is that this point, the another point, is very close to the point where we'll find the instantaneous velocity at. So we plug this point into the function. The function is defined here. So we have 1.01 cube plus 1.01 minus, we plug 1, so we get 1 cube plus 1 all over 1.01 minus 1 is 0.01. Now we compute this, and this should give us, using calculator, we have 4.0301. That's the instantaneous velocity at time t equals 1. Now if we choose another point, but closer to the point 1, t equals 1, if we choose 1.0001, this should give us better approximation. This should give us something like 4.0, maybe 20 something. So you can compute it at this point. So you should get a better approximation than this, because this point here is closer to t equals 1 than this one. If you add more zeros here, you get even better approximation. So that's the instantaneous velocity. We try to find a point that's very close to the given point and find the average rate of change. Now we want to calculate, in this example, the average rate of change of the function f of x equals x squared minus 3 over the interval 1, 8. And then we find the instantaneous rate of change at x equals 2. So let's start with the average rate of change. Here we use the formula f of b minus f of a over b minus a. F of b, what is a, what is b? A is 1, b is 8, so f of 8 minus f of 1 over 8 minus 1. Now we plug these values here. F of 8 gives 8 cubed minus 3 minus f of 1 squared minus 3 over 8 minus 1. And then 8 cubed minus 1, after plugging this value, we get 8 cubed minus 1. Let's use calculator. Okay, so minus 3, this is 509, minus 1 squared minus 3 is negative 2. We have plus, so we have 511 over 7. And this gives us 73. We can use some, if we are talking about time, or if that means, or velocity, that we can use some unit. But here we are not specific, we don't have specific units, so we don't need to worry about that. Now let's find instantaneous rate of change. To find this is average rate of change. Now we want to find the instantaneous rate of change. And as I mentioned, instantaneous rate of change is just an approximation, is just an estimate of that value. And next time when we talk about derivatives, we will use that instantaneous rate of change, and we will apply limit to get a better or more exact value as an estimate, or as actually we get exact value for that, for the the tangent line, because we take limit very close to we get x very close to a if we make this distance goes to 0. So when we take limit as x approaches a, that means it's very close to a, sufficiently close to a, then we get an excellent approximation. So we'll talk about this next time, but for now we are focusing on instantaneous rate of change as an estimate of the slope of the tangent line. Now, for this reason, we are studying the instantaneous rate of change at x equals 2. So this is A. Now we need another point, so let's choose B equals 2.001. We pick this value. You can choose any other value that is very close to 2. You can add more zeros here to get better approximation, or you may use 2.01. It's up to you. Now we apply same formula as in the average rate of change case. So we get f of 2.001 minus f of 2 over 2.001 minus 2. Now plugging these values we get, and using calculator we get 4.001. Now as you can see, average rate of change need not be equal or very close to instantaneous rate of change, because those are just estimates, and as we've seen in previous examples, this may be L1, this is an estimate of this line, but that's not a good, of the tangent line I mean, but that's not a good estimate. But this one is better estimate. This is L2. Let's say this is the line that we obtain when we apply this point 2.001. We get a better approximation or estimate as we get approaches the specific value x equals 2. Now the third example here, we have the following table shows daily crude oil production by Pemex, Mexico's national oil company, for 2008 to 2013, T in years. So we start at 2008, and that represents T equals 0. Then this is 2009, 2010, 2011, 12, and 13. So instead of writing these, we just use 0, 1, 2, 3, 4, and 5. And the daily production in million barrels is here. In 2008, we have 3.116, and in 2009 we have 2.97, and so on. So we want to compute the average rate of change of P of T, the production, over the period 2008 to 2011. I mean from here to here. Now how to find average rate of change? We apply a formula. So let's use f of 2011, the final point, it's 3, minus the initial point, it's 0, over, okay, so sorry about this, this should be the value of t. So this is the denominator. Those are the t values, and those are P of t. So we have P of B minus P of A over B minus A. Now what is production at B? What is the final point? The final point is 3. So P of 3 minus, what is the initial one? It's 0. So we find P of 0 over 3 minus 0. What is P of 3? P of 3 is 2.94 minus P of 0. P of 0 is 3.16, all over 3 minus 0, 3. Now we use the calculator to compute this. 2.94 minus 3.16 divided by 3 is negative 0.073. This is just an estimate. So this is the average rate of change. And production. or daily production. Now we can study the instantaneous if we know some formula, but here it's not easy to do that because we don't have a formula. So this is what we mean by average rate of change and what we mean by instantaneous rate of change. For average rate of change we focus on an interval, but for instantaneous rate of change we focus on approximating the slope of the tangent line at a specific point. So we choose a point that's very close to the given point, and we apply same formula, the formula that's used to find the slope. Now a very important point here I want to focus on before we end this video. Instantaneous rate of change of the function f of x at some point x equals a was computed using the same formula as the slope, but this is what we call the derivative of the function, and we'll talk about this next time. So instantaneous rate of change is the same as the derivative, as we'll discuss next time. So that will be the section 3.5.